Hi, in this video I'm going to continue on the topic Industrial Chemistry, and here we will be stepping into the topic activation energy. So let's get started. Now first of all, refresh your memory about what we have learned in rate of reaction. We learned something called collision theory, and according to collision theory, we say that a reaction is a result of effective collision. By effective collision, it means that the reactants must be colliding with the correct orientation as well as they are colliding with sufficient energy. Now, the so-called sufficient energy is actually called the activation energy. So down here, I want you to underline this definition of activation energy. So here, activation energy is defined as the minimum energy that the colliding species needed for effective collision and therefore leading to a reaction. So this activation energy basically tells you the minimum energy required in order to bring about a reaction. Okay? Now, in other words, here we say that the reactant must overcome such an energy barrier. So sometimes activation energy is described as the energy barrier because the reactants must be able to overcome this energy barrier in order to lead to a reaction, right? So it is also known as the energy barrier. Now, you can also tell if the activation energy is very high, meaning that the energy barrier is more difficult to overcome, then the reaction rate will be slower because the reaction will be harder to proceed. Okay? So you see, the higher the activation energy, the slower the reaction because fewer colliding molecules will have energy equal or greater than the activation energy. Okay? So that makes sense. Now down here, energy profile is a graph or is a curve describing the energy of the reactant as the reaction proceeds. Now here, the y-axis is the potential energy, basically the energy possessed by the reacting species, and the x-axis will be reaction coordinate. Reaction coordinate basically means the progress of reaction. So from left to right, it is changing from reactant to product. Okay? Now, you notice that there is a curve. Now, when you look at this curve, you can imagine that you are moving a sphere or you're moving a ball up the hill to the destination here. Okay? So if you want to move this ball to here, what you have to do is to push up the ball so that it can overcome this mountain, overcome this hill, so that it can roll down. Now the question is, how tall? The question is, how high you need to push this ball up so that there is a chance where the ball can roll to the product side. Now, if you push the ball to this height, do you think the ball is able to roll forward? Well, probably not. Once you release your hand, the ball will roll back to the original state. Okay? So, only when you push the ball up to here, at this point, then the ball will have a chance to roll forward, resulting in the product. Of course, there is also a chance where it rolls backward and goes back to the reactant, but at least you can tell. At least it has to have such a potential energy in order to lead to a reaction. Okay? Now, what if you push it all the way up to here? Well, of course, it can also lead to a reaction, but it's not necessary. Okay? So you realize that the minimum height of which we push the ball up in order to bring about a reaction will be here. So this blue arrow here is what we call the activation energy. Activation energy. Okay? The minimum energy required to bring about a reaction. Okay? Now you notice that there is another term called enthalpy change. Basically, enthalpy change tells you the energy difference between the reactant and the product. Now, even though the enthalpy change is shown by this arrow, and you notice that even though we push the ball up to the point where it has sufficient energy as shown by the enthalpy change, well, it doesn't suffice to bring about a reaction. It is not enough to bring about a reaction. So, in other words, enthalpy change has nothing to do with activation energy. You can have a small enthalpy change, but a large activation energy. So, you need to make sure that you sort these two concepts out. Enthalpy change tells you the energy difference between reactant and product. That would account for the amount of heat released or the amount of heat absorbed after the reaction. Activation energy, on the other hand, tells you the minimum energy required to bring about a reaction, and activation energy has to do with the rate of reaction. Okay? So make sure you can sort these two terms out. Okay? Now down here, so you notice that, first of all, energy of the reactant is lower than the product. That means it is an endothermic reaction with a positive enthalpy change. This one we have talked about it before, just to refresh your memory. Now down here, the reactant must reach certain energy in order to react to form a product, and such an energy barrier is called the activation energy, EA. Okay? Now, the third one, you also have to pay attention to that. If the reaction is reversible, then the backward reaction will follow the same energy profile, but going backwards. So, if this time we have the ball here, because now we want to do a backward reaction, that means the product will become the reactant, then it will actually travels along the same curve, or it has to overcome the same mountain, same hill. But you can notice that if it undergoes a backward reaction, the activation energy will be this one. This is the activation energy backward. And you can tell it requires less amount of energy to go backwards. Okay? So you can tell the backward reaction will proceed faster. Okay? Okay, next page. Next page, we have a practice question. So again, spend some time working on this and resume the video and check the answers. Okay, let's have a look. We have an energy profile here. A becomes B, and then there is two energy terms, X and Y. So express the followings in terms of X and Y. So enthalpy change of forward reaction. So enthalpy change of forward reaction, we are talking about Y here. Okay? And you can tell the product is having lower energy than the reactant, implying that it is an exothermic reaction. So make sure you put a negative here. Okay? Now, enthalpy change for the backward reaction. So from B back to A. Now actually, the enthalpy change should be the same. The magnitude should be the same. However, the sign should be flipped. So this one should be positive Y. Okay? Remember, enthalpy change, no matter if it's a positive or negative, endothermic, exothermic, especially endothermic, even though it's positive, but you need to include the positive sign. Okay? Now, activation energy of forward reaction. So from here to here, the minimum height of which the ball needs to be pushed would be X. Okay? So this one is X. Okay? And activation energy for the backward reaction. So pushing the ball from here to here, you need to overcome such a huge height, the huge energy barrier. So this one should be X plus Y. Okay? Now remember, energy is a scalar quantity, so that must be positive. You won't have negative energy. Okay? However, enthalpy change here, the positive negative is talking about exothermic, endothermic. It's not about the, whether it is large or small. Okay? We're talking about exothermic, endothermic. So that's why we need to include the negative and positive signs. Now down here, the following hypothetical reaction is elementary. Now elementary basically means one-step reaction. One-step reaction. So you don't have to take care about whether it has a two-step, three-step, multiple steps. No. Okay? And it has an enthalpy change being positive 27 kilojoule per mole, and the activation energy being positive 54 kilojoule per mole. Actually, activation energy no need to have the positive sign, but anyway. Now sketch an energy profile and also label clearly enthalpy change and activation energy. Okay. So first of all, make sure you remember the y-axis and x-axis. So the y-axis is the potential energy. And then the x-axis would be reaction coordinate. And since it is an endothermic reaction, so the product should have higher energy than the reactant. So I will have the reactant here, which is M plus N, and then I may have the product here, which is O and P. Okay? And then now the profile should contain a curve consisting of one activation energy. Now, the reason why we have one activation energy is because it said that it is an elementary reaction or one-step reaction. So there is only one step. For each step, it has one activation energy. That means if it is a two-step reaction, then that would be two activation energies. I can put down here. So we can add a remarks here. If we have a two-step reaction, then the energy profile will be like this. Okay? So you see, this one will have two activation energies because there are two steps. If there is a three-step reaction, then there will be three activation energy. Okay? Now, anyway, let's go back to here. Now we have to label the enthalpy change. So the enthalpy change basically is the energy difference. So from here to here. Okay, so you can see this one, the red one is the enthalpy change, positive 27 kilojoule per mole. And then the blue one is the activation energy, 54 kilojoule per mole. Okay. Now, next page. Maxwell-Boltzmann distribution curve. Now, first of all, we want to talk about how temperature affects the rate of reaction. So you know, first of all, temperature is the average kinetic energy of molecules. So make sure you know the definition of temperature first. We are talking about average kinetic energy of molecules. Now you notice that we are talking about average. That means for a given temperature, like room temperature, we have different molecules having different kinetic energy. Some may be having a higher kinetic energy, thus moving faster. Some may be having a lower kinetic energy and therefore moving slower. So we are talking about average kinetic energy. And down here, the Maxwell-Boltzmann distribution curve basically describes the distribution of kinetic energy among these molecules. Okay? So distribution of kinetic energy among these molecules. Now you notice this distribution curve. This one follows a normal distribution. Normal distribution. You can mark it down. It is following a normal distribution. What do you mean by normal distribution? Now, a normal distribution basically means that you have high values, you have low values, you have maximum, you have minimum. But you can tell the majority of the molecules or majority of the items here should be having a medium or a mediocre energy. Okay, so you notice that here the y-axis is the population of particles, and the highest population will be having a medium or mediocre energy. And you notice that the two extremes will be having a very low population. Okay, so if a curve showing you such a distribution, then it is called normal distribution, and it is signified by this bell shape. Okay, so Boltzmann distribution curve is having a normal distribution. Okay, now regarding the curve, notice that few molecules have very low energy values. You can tell, Also, few molecules having very high energy values. So like I said, the extremities are often the minorities. Now, most molecules are having a moderate or mediocre amount of energy, as you can see from here. The highest point on the curve shows you the most probable energy. So the majority of the molecules are having like such an energy. Okay, the curve on the high energy end never touches the x-axis. Can you notice that here? So it never touches the x-axis. Okay, when you are asked to sketch the Maxwell-Boltzmann distribution curve, make sure that you have the curve not touching the x-axis. Okay. Also, here, this is also important. The area under the curve is telling you the total population of particles. Okay. Now, because this normal distribution curve, you can understand it by like a bar chart, But when the bar chart is having so narrow width, that means they take into account every single kinetic energy, like 1 joule, 2 joule, 3 joule, etc. Then altogether this bar will form like a curve. Okay? So if you think about the area under the curve, basically with all the bars added together, that basically tells you the population. Okay? Now, if you don't understand it, basically the area under the curve tells you the total population of particles. If you have more particles in the sample, then this curve should have a larger area. Okay? Now, why do we have to look at this Boltzmann distribution curve? Because this curve can be used to explain the effect of temperature and also the effect of catalyst on the rate of reaction. Okay? Now, you notice that in our core topics, when we talk about rate of reaction, we say that temperature will affect the rate of reaction. The higher the temperature, the faster the reaction. Now, in the core topics, we use collision theory to explain. We say that at a high temperature, the particles are having a higher average kinetic energy, so they will be moving faster, leading to more collision. They will be heating harder, okay, when they collide. So the two factors account for the faster reaction because they are having a higher frequency of effective collision. So this is what we talked about in the core topics. But actually, the effect of temperature on rate can also be explained using the Boltzmann distribution curve. So we have like two explanations as to how temperature can affect the rate of reaction. Now, catalysts. You notice that collision theory is unable to explain how catalysts can speed up the reaction, right? The catalyst doesn't increase the collision frequency, doesn't increase how hard the molecules collided with each other. But here, using the Boltzmann distribution curve is able to explain how catalysts can speed up the reaction. So that's why we have to learn this new concept. Okay, let me break it down for you. So down here, effect of temperature on reaction rate. Now, if you look at this curve, you see we have a blue curve, we have a red curve. The blue curve is having a temperature T1, which is lower. And then the red one is having a temperature T2, and T2 is hotter. Okay? Now, when you look at this curve, you notice that for T2, the curve is sort of shifted to the right-hand side, shifted to the higher energy end, right? How can you tell it is shifted? Well, you can pay attention to the maximum point. So you see T2, the maximum point is here, whereas the T1, the maximum point is here. So when you see the maximum point is lying more to the right-hand side, then we say that the curve is shifted to the right-hand side. Now, shifted to the right-hand side, meaning that the average kinetic energy of molecules has increased. Okay? Now, you also notice that we have something called activation energy. So the activation energy basically tells you the minimum energy required to bring about a reaction. So here the activation energy is shown here. Basically, it tells you that any molecules having energy equal to this energy or greater than that, which is on the right-hand side of these green boundaries, then they will have enough energy to overcome that energy barrier. Okay? Now, if you look at the blue curve, then the area under the curve of which the energy is higher than the activation energy is shown by this shaded area. And when you compare to that of the red curve, obviously the red curve is having a larger area. That means there will be a greater proportion of particles having energy equal or greater than the activation energy when the temperature is higher. And that accounts for the reason why when temperature increases, the reaction goes faster. Okay? So down here, you can underline keywords, and I want you to look at how I describe or how I explain, because these terms are frequently used when you are explaining situation using Boltzmann distribution curve. Now you see, at a higher temperature, there will be a greater proportion of particles having energy equal or greater than the activation energy. Okay? You notice we always say energy equal or greater than the activation energy. Okay? And down here, this is talking about the collision theory, and in addition, so particles having greater kinetic energy, they will move faster and collide more frequently. So this one is the collision theory. So it results in an increase in frequency of effective collision. So you notice that we have now two tools, two concepts to explain how temperature affects the rate. But at the end of the day, it will increase the frequency of effective collision, okay, and therefore faster rate. Okay, right. Now, one more thing you have to pay attention, especially when you are asked to sketch graphs. Now, when you are sketching T2, not only you have to sketch the graph so that it shifts to the right, but also pay attention that the area under the curve must be more or less the same. So that's why when the curve shifts to the right, the peak, okay, the height of the curve will be shorter. You see, this one is higher than this one because as it shifts to the right, the curve becomes bulkier, becomes fatter. As it becomes fatter, then it should be shorter. Make sure, if you want to make sure that the area under the curve is the same, okay? And also make sure that you do not have the line touching the x-axis at the high energy end, okay? And it is okay to hit the 0 point because you won't have negative energy, okay? Now also pay attention, even here I use a bracket, but you can make an amendment here. You should always put down kinetic energy. You should always put down kinetic energy. Okay? Alright. Let's have a look at this practice question and try it yourself first and resume the video once you are done. Okay, let's have a look. So 25 degrees Celsius, we have a Boltzmann distribution curve. What is the significance of the area under the curve? Well, it shows you that the population of height. Now, sketch on the same graph the shape of the curve at a higher temperature. So at a higher temperature, we are expecting a rightward shift. So like this, okay? Right, and down here, with reference to the curve sketched in B, explain how an increase in temperature affects the rate of reaction. So, you can see, if you look at the activation energy here, so obviously the area under the new curve, of which it is higher than the activation energy, is higher than that when compared to the original curve. Now, how would you write down, how would you describe this observation? Okay, so first of all, we need to describe something with reference to the curve. So you want to compare the area, right? Okay, we say that so this is what we observe from the graph because they ask us to explain it with reference to the curve. So after we indicate the difference in observation, then we will explain, we will say that, therefore, okay? So this is how we explain the effect of temperature on rate of reaction using the Boltzmann distribution curve. Okay, next page. Now, we want to look at how catalysts affect the reaction rate. Now, first of all, again, you have seen this definition many times. A catalyst can alter the rate of reaction without itself undergoing permanent chemical changes. Okay? Now, this time, if you look at the Boltzmann distribution curve, we only have one curve because now we are not talking about two different temperatures, so only one curve. But now we have two activation energies. We have a EA1 and EA2. Now, basically, the EA1, the green one, is the one without the catalyst, the original one. And now, with the catalyst will provide an alternative reaction pathway of which it has a lower activation energy. So now the EA2, you can see the requirement of energy is much lower. Okay? So you notice that here, a positive catalyst provides an alternative reaction pathway that has a lower activation energy. So the EA2 is the alternative reaction pathway activation energy. So you notice that this sentence is similar to what we talked about. A greater proportion of particles will have energy equal or greater than the activation energy 2, and therefore the reaction is faster. Okay? So remember, a catalyst doesn't change the original activation energy. You notice that the EA1 is still there. So the original reaction path is still there. But a catalyst simply providing a shortcut, simply providing an alternative reaction pathway. And if the reactant goes for the alternative reaction pathway, then the activation energy is lower. So you can tell in reality, of course, most of the reactant will go for the alternative reaction pathway. Therefore, it will be leading to a faster reaction. Okay. Now down here we have an example. So hydrogen peroxide decomposes into oxygen and water in one step by itself, but this is pretty slow by itself, you can tell. But if we provide it with bromide ion, then the reaction goes much faster. So you see now the reaction takes place in a two-step mechanism, leading to the same product. You notice that the bromide, H+, can all be cancelled out at the end because they are the catalyst. Also the bromine can be cancelled out. Okay? Now, the second step, the second reaction pathway is faster, so you can tell the activation energy is lower. Now, if you look at this reaction profile, now the original curve is shown by the red one, so only one hue, that means one step, and the activation energy is super high here. Okay? Now, for the catalyzed pathway, you see now it has two steps because there are two hills. So when you have two hills, two mountains, you will also have two activation energies. Okay? So here, but you notice that no matter you notice that even though we do two steps, the activation energy is still lower than the original. Okay? Think about when we have to push the ball up to here. Even though you push the ball from here to here, it is still lesser than the original. Okay? So that's why the green path, the catalyzed pathway, is faster. Okay? So you notice that, okay, bromide ion and hydrogen ion act as a catalyst. They provide alternative reaction pathway with lower activation energy. Okay? So you notice that if the question asks you to sketch the energy profile for a catalyzed pathway, you need to pay attention whether there are two steps or three steps. Usually it is more than one step. So usually it starts with two steps onwards. So if you're asked to sketch energy profile of a catalyzed pathway, it will be best if you make two hills with two activation energy. Okay, but make sure that the catalyzed pathway will have the activation energy lower than the original one. Okay, so this is how we explain the effect of catalyst on reaction rate using Boltzmann distribution curve. Again, we have a practice question. Pause the video, attempt it yourself. Okay, here, with reference to the curve, how catalysts affect the rate of reaction. So here, with the catalyst, we have a new activation energy, EA prime. Okay, so first of all, we have to use the definition of the catalyst. So we say that the catalyst okay. So we say that the proportion
of particles having kinetic energy equal or greater than EA1 is larger than that of EA, okay? The original, the activation energy of original pathway.
Okay, so this is how we explain it. Again, we have to compare the proportion of particles having kinetic energy equal or greater than the activation energy. But this time we are using the activation energy of the alternative pathway. Okay. Now question 2 down here. We have an iodine chloride reaction, and this is the main reaction. And in the presence of Fe2+, the reaction is catalyzed in. Now you have to construct a potential energy level profile, basically the energy profile, for catalyzed and uncatalyzed reactions, indicate that the activation energies of both pathway and also the enthalpy changes of both pathways. Okay. So first of all, this is potential energy. Then we have the reaction pathway, the reaction coordinate. Okay? And then, no matter what, we have the same reactant, same product. So, I'm not sure whether it is an endothermic or exothermic. I will say that it is an exothermic reaction. So, 2 minus here, 2I minus here. Let's just say this are the products. So we have 2 SO4 2 minus and also I2. Okay. So the original pathway, very simple. Would be like this. Okay, this is the original pathway, uncatalyzed pathway. And if this is catalyzed, then there should be 2 curves. Because now there are 2 steps. Okay? So here we have the intermediate state. Now at intermediate state, what do we have? You have to follow the steps. So you notice that S2O8 and Fe2+ react to form SO4 2 minus. Okay, so you do have the SO4 2 minus here, but you also have the Fe3+. Okay, so you also have the Fe2+ here. Okay, and you also have the unreacted iodide ion. Okay, right, and at the end here we should also have the Fe2+. Okay. Now, then you have to show the activation energy. So the activation energy, so for here, the original one, this is the EA1, okay? And with the catalyzed pathway, so the EA is over here. This is the activation energy, EA2, okay? This one is the catalyzed pathway. And you can clearly see that EA2 is smaller than EA1. Okay. For the enthalpy changes, no matter a catalyzed pathway or uncatalyzed pathway, the enthalpy change is the same. So the delta H is over here for both pathway. Because you know that catalyst only affects the rate of reaction. It has nothing to do with the enthalpy change. Enthalpy change should be the same. Okay? So I will stop the video here.